All right, we are going to work example 5 two different ways. It's a two-parter. We know how to do three things now, and they're all kind of the same, right? Find the antiderivative of something, solve a differential equation, and now what? Integrate, right? Integrate. So in example 5, it says to find the particular solution to the following differential equation. And yeah, again, you didn't have to tell me it was a differential equation, right? I see the equal sign. You can see it. But what's different about this one is it's equal to not a first derivative, but a second derivative. And because it's in terms of y, the solution means getting back to y equals some function of x, okay? We call this the second order differential equation. Now in part A, I have two initial conditions, which is kind of nice because when I find the antiderivative of the second derivative, I go to the first derivative. And then I do it again to get to the function. And notice I have an initial condition that satisfies the first derivative. And I also have an ordered pair that satisfies the original function. So let's go ahead and find the antiderivative of the second derivative. So we're going to do that, again, using our new notation. I'm going to take the what of both sides? Integral with respect to x. And if you have more than one term, like we do on the right side, go ahead and put it in parentheses. So there you go. You got your left bookend and the right bookend. Now on the left side, the antiderivative of y double prime essentially is y prime, or in this case, dy dx. Do I need to put a plus c sub 1 over there? No. Yeah, and I'm not going to either. Good. Now on the right side, we just have three little terms. Power rule, power rule, power rule. So 12x squared becomes, bless you, add 1, right? And then divide. We're not taking the derivative. We're integrating. 4x cubed. Good, because you get x cubed, then you divide by the new cube. 12 thirds is 4. 6x to the first becomes something x squared. Divide by 2, you get 3. Good. Minus 4 becomes x, right? 4x, and then plus c. Now the question is, do I just do it again immediately, or do I find c before I proceed? I think I should find c because on part A I have an ordered pair that satisfies the first derivative. So let's just copy this and paste it over here. And bless you. So we'll say, how about when y prime of 1 equals 3, we get the derivative is 3 when y is 1. So we'll plug in a 1 and we get 4 plus 3 minus 4 plus c. And if we carefully solve for c, we get c equals 3's cancel, 4's cancel, we get 0. Oh. So dy dx equals 4x cubed plus 3x squared minus 4x, bless you. And now there's no plus c there, but it's not because we forgot to write it. It's because it's 0 in this particular case. All right, so much fun. Let's do it again. I'm going to go ahead and throw the integral here and sneak it. Throw the integral there and sneak it like that. Oh, that's not the best effort I can make, but it works, right? What becomes of the left side? The antiderivative of the first derivative is y. Don't need a plus c, because we're going to do that on the right side. And one more time, antiderivative. 4x cubed becomes x to the fourth, and we divide by the new exponent 4, and 4 fourths becomes 1. Plus 3x squared, that becomes x cubed. Divide by 3, they divide out, and you get x cubed. Minus 4x squared becomes, 4x becomes x squared. Divided by 2, you get 2. And now I can put plus what? Can I reuse c since I already found it up above? C sub 1, C sub naught. Yeah, you can actually reuse c here if you wanted to, just plain old c, because you've already reconciled it up above. But when in doubt, you know, it's good just to maybe use something different. I'll use c sub 1. I'm going to use k. I like k. All right, now I got to find k, or your c, or whatever it is, and here's the initial condition that satisfies the solution equation. So when y of 0 equals negative 6, we get negative 6 equals 0 plus 0 minus 0 plus k. And now that we have our k, we can go ahead and say so, and then we come back up to the previous line. Y equals x to the fourth plus x cubed minus 2x squared minus 6. And that right there is the solution. It's the function whose second derivative is 12x squared plus 6x minus 4 that passes through the ordered pair 0, negative 6 and has a slope of 3 at y equals 1. Nice. Okay. That's only part A, though. Good thing. I was hoping we weren't done. Part B, same second derivative, same second order differential equation to start with, but now notice the two pieces of information we have. Neither one of them tell us anything about y prime, are they? They're both about the solution equation. So I can come back down to this line here, but I can't really do anything else. I can't find c. So I guess I do what I only know what to do or can do, and that's to find the antiderivative of both sides again. And I will treat c just as a constant. And what becomes of the left side again? Y. And 4x cubed, the terms are going to be the same, right? X to the fourth plus x cubed minus 2x squared, anti-differentiating, adding 1 and dividing, plus cx. Good. Now can I use the same plus c here? No, this is where you would definitely have to come up with some different variable because the coefficients of the constant and the x are not necessarily the same. So I'll use k again. Okay, so now I have two unknowns and I have two pieces of information. Yay, lucky me. Which ordered pair would you like to plug in first? 0, 4 or 1, 1? 0, 4, okay. So at 0, comma 4, that's another way to do it. You get 4 equals 0 plus 0 minus 0 plus 0, are you keeping track? Plus k. How convenient. K equals 4. And now we can say at the point 1, 1, we get 1 equals 1 plus 1 minus 2 plus c times 1 is c plus our newly discovered value of k, which is 4. Now we have one equation with one unknown. Good things happen. We get 1 equals, that's 2 minus 2, that's c plus 4. So c equals negative 3. Are we done? If we box up our k and we box up our c, are we done? No, not quite. We have to solve the differential equation, so we have to write the final equation. So y equals x to the fourth plus x cubed minus 2x squared minus 3x, stay with it, finish, as Nick Saban says, finish, plus 4. Right, if you would have plugged in your c for k and k for c, that wouldn't have been finishing. That would have been wrong. Oh, yeah. Yeah, you would have. Yeah, you would have. But you would have been stuck on that line because you would have had one equation with two unknowns. Then you would have plugged in the y-intercept and gotten your value of k and then back solved. So, yeah. The order in which you plug in doesn't really matter. As long as you plug them both in, you'll have enough information. It could be that when you plug in both, you get two equations with two unknowns, and then you would solve them simultaneously, one with your right hand, one with your left hand. Is that what that means? No, you would like use substitution or elimination method. Yeah. Okay. All right. So second order differential equation done a little bit differently each way, but again, solving a differential equation means getting back to the original equation, the original function, in this case y. All right, so as we were taking the antiderivative of these expressions, we were using the power rule. The power rule, as it turns out, is like one of the only rules that applies broadly to things of at least the same form, but we can apply it in a bunch of different cases. Other than that, finding antiderivatives comes down to this, right? Recognizing known derivatives and then working backwards. Unfortunately, there will not be a time in here where you show up one day and we do like a Hody-High rule for integration. Darn. There's no quotient rule for integration. There's no product rule for integration. Integration just requires you to kind of recognize the integrand as something that you can find the antiderivative of or something that you know to be a derivative of something else. And if it doesn't fit something you recognize, then you might have to algebraically manipulate it, do something clever, like multiply by a clever form of 1, add a clever form of 0, to get it to look something that you do recognize. So on example 6a, that's what all of these are about. So walking up to this problem, we got the integral with respect to x of the integrand. So there's the expression. Now I'm looking at that and I'm saying, oh yeah, I remember that time Mr. Corpy had us memorize that thing that when we took the derivative we got that. Right? Y'all remember that day? That was a nightmare, I think. I don't think that really happened. I think that was in my dream, which was a nightmare, because I don't think we memorized that. If we did, you have a lot of space in your brain and a great memory, because I don't know what it is. So what we're going to have to do is manipulate that into something that we recognize. Can we just do the power rule in the bottom? I'm kind of leaning that way, because I'm desperate. Do methods increase in their chances of being correct in direct proportion to your level of desperation? No. Let's see. The Hody High rule. No, it doesn't exist. Okay. Any ideas? Right. Yeah, you could do that. Here's what you could multiply by the radical over the radical, because that's really equivalent to what? 1. So you can manipulate your expression. Here's what I would do to start. When nothing else works, just kind of like, when you pick up hitchhikers and you have a truck, nothing's more annoying than when they want to ride in the front in the cab with you, right? It's like, get in the back. You're a rider. You're not supposed to be in the front bothering me. You have no influence on where we're going, how I'm driving. Just get in the back. So pull your constant multiples out front. That's kind of what I'm getting at. Yeah. Yes. Now you got a 1 minus x squared to the 1/2 in the top, and you can even pull out a factor of what in the bottom? A 3, which can then go out in front, in the back of the truck essentially, with the 5, and you're left with a 1 minus x squared. And don't forget your dx at the very back. It's pretty easy to do. Now, just putting that in parentheses and putting a 1 there may draw your attention to something else that we can do, right? 5/3 is just going along for the ride now. What can we do with our exponents there? Subtract them, because the bases are the same, and you get 1 minus x squared to the 1/2 minus 1, which is negative 1/2. So that's already looking better. Can we use a power rule on the inside here now? No, because it's raised to the negative 1/2 power. Is there a way to expand that, like square multiply double square? No. Yeah, y'all are already there. Good. I can't play dumb for very long. We'll bring that back on the bottom and put it back under the radical, and we get this. And now that should be slapping you in the face, saying, here I am. And you're like, man, you would do great at a masquerade party, right? Because I did not recognize you in the beginning. Mr. What'd you say? Arc sine. Very good. 5/3 arc or inverse sine, either one, of x. We don't need 2 x's. And then, of course, you finish it off with plus c. There you go. Little manipulation goes a long way. You have to be able to manipulate it into something you recognize. And that's why example 6 is so much darn fun. So, rather than me go on your vacation and just tell you how it is from afar while you stay at home, stealing your fun, I'm going to let you have the fun. You go ahead and jump in on B and manipulate it until it's something you recognize, and then find the antiderivative. You may begin. Have a good trip. See you next fall. Yes. Is it working or is it not charged? Oh, man. You want to use paper or do you want to go to the hub? You want to take care of it? Yeah. Good luck. So close! There it is. Don't be a statistic. Oh, you're a statistic. Oh, that's a different class. Don't be one of those people who loses a point for little things that you shouldn't be losing points for. Well, first of all, you're missing the finishing thing off to the side, but that's the wrong antiderivative. You could do that in the bottom. That's one of your options. This becomes like a little miniature trig proof inside of an integral, but you don't know what the target is. You're just kind of like, as Charles Darwin said, a blind man in a dark room looking for a black cat that isn't there. Yeah. And then Escalante quoted it in the movie. Yeah. Yes! Yes! Yes. 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 Okay. So, I don't think looking at that, it's immediately obvious what you take the derivative to get that. So what are some of the options? Well, whenever you have squared trig functions, you should be at least considering the PIDs, right? You got Papa PID and Baby PID 1 and 2. So cosine squared is 1 minus sine squared. Will that help? Well, you're not going to be able to split up terms in the denominator. 1 minus sine squared is a difference of squares, so that's 1 minus sine times 1 plus sine. Would that be helpful? Maybe not. So what else can we do? Well, we can write everything in terms of sine and cosine. It already is. Okay, that doesn't help. We could bring the cosine squared to the top and call it secant squared. But then it'll be sine times secant, and you can't just take the antiderivative of each factor because there's no product rule. So one of the other options is to just split up the factors like that and use the associative property of multiplication. So if you do that, 1 over cosine is known as secant, and sine over cosine is known as tangent. Don't forget your dt. And now you're like, oh, it's secant tangent. Secant tangent is the known derivative of secant of x, or in this case, secant of t. And then, of course, we are not done. We put plus c, and we keep those points. We don't become a statistic. All right, plus c, plus c, plus c. Excellent, excellent, excellent. You ready for another? Yeah. Letter C. On your mark, it said go if you haven't gone already. Some of y'all went. Cormac McCarthy. Yeah. It's a good book, yeah. It reads kind of interestingly. He's got an interesting writing style. Yeah. Yeah, it's a quick read too. Yeah. Yeah. Are you control? Oh. I thought that was like ESPN footage. Are you winning? No. Oh, okay. All right. Hey, does it matter that it's P with respect to P? Is that throwing anyone off? No. As long as the variable of integration, dP, is the same as the one in the integrand, it's like it was x dx, t dt, p dp, doesn't matter. We'll just kind of use some different variables to get you accustomed to using them. Yes, good, perfect, yep. Sine squared, cosine squared, sine squared. Excellent. Now you're ready to execute it. You saw the insight. You got the insight. So do you. Yeah. Sure. Okay. You walk up to the problem and you might be like, hey, that second term plus 4 I've got it. It's going to be 4p, right? And then, of course, the plus c. I've got that. But tangent squared, that's one of those ones that you think might be a derivative of something, right? So you quickly scan your mental catalog of derivatives of trig functions, and you don't find it, right? You're like, oh, man, I was thinking maybe it was what? What's the one that's most maybe closely related to tangent squared when you scan your derivatives? Secant squared. There's a secant squared in there. So at some point you're like, I know that the derivative of tangent is secant squared. Hey, I remember now because it's a squared trig function. There's a way to relate secant squared to tangent squared, right? You got to know your PIDs. And baby PID number 1 is 1 plus tangent squared of x equals secant squared of x. So if you solve that, you get secant squared of x minus 1 is tangent squared. And so you could do a substitution. Now, instead of integrating that little piece there and trying to have the burden of, some terms that haven't been integrated yet and some that are, we'll just leave it in there and integrate all at one time. Secant squared of p now minus 1 plus the 4 dp. You can either do that or split the 4 up and call it 3 plus 1 and then replace tangent squared plus 1. Either way, you come up with secant squared of p plus 3 with respect to p. And now you've got it, because the antiderivative of secant squared is tangent, and the antiderivative of 3 is 3p, and then plus c. And there's your answer. So, you might want to make a note here. Anytime you're trying to find the integral of tangent squared or cotangent squared. Cotangent squared you can relate to cosecant squared, and cosecant squared is a known derivative of cotangent. You'll just be off by a negative. So anytime you're integrating tangent squared or cotangent squared, it's going to involve a baby PID substitution to put it in terms of either secant squared or cosecant squared, which are doable. So file that up there under strategies, right? Strategies. Okay, many of y'all had that as I was walking around. Let's do one last one right here. Part D. We're integrating with respect to m, but our integrand has m's in it. M's. Haven't seen those in a while. Now, what I would do first is I would pull that 3 out front. That's just kind of what I typically do. If there's a constant multiple there, I know he's there in the beginning. I know he's going to be there in the end. I throw him out front. He doesn't influence what I do. Cosine squared of m halves. Well, cosine squared is 1 minus sine squared, right? But if I do that, I can handle the 1, but the sine squared is going to put me in the same boat as the cosine squared. And that's the boat right now that's sinking. Are there any other identities we can use? We can call cosine times cosine. You know what? I don't like that. I don't really even like that the angle is m halves. That's kind of like a chain rule. We haven't really done any chain rule stuff yet. How would you? Yes, very good. They're all related to those. We call them the power reducing identities. The power reducing identities. And you do need to know these. These are BC identities. Here they are. We'll do the cosine one first. Cosine squared of x is equal to 1/2 1 plus cosine of 2 times x. And they do come from the double angle identity for cosine. And then the sine squared is very similar, but because it's not in terms of itself, it's in terms of cosine, it's 1 minus cosine of 2 times x. We'll be using these quite a bit towards the end of the year when we get to polar area. We're going to be finding polar area. But right now, we're going to use it to rewrite our integrand. So here we go. Cosine squared becomes 1/2, parentheses, 1 plus cosine of twice our x. What is our x? It's m half, yeah, 1/2 m. So I'll just put m halves right there. with respect to m. Now that's pretty cool. The 1/2 now out front of the integrand can come out front of the integral. Grr. And then I'm left with parentheses 1 plus cosine of 2 times m halves. That's just m. Oh boy. Now we've got it, don't we? 3/2 goes along for the ride. Beefy purple brackets. Now, I think this is an occasion for the brown. Beefy brown brackets. What's the antiderivative of 1 with respect to m? M, right, or x. And the antiderivative of cosine? Is it sine? Is it negative sine? Yeah, sine, right? Guess, check, revise. If you think it's positive sine, what's the derivative of positive sine? Positive cosine. Yeah, I'm good. Now, where do we put the plus c? Here inside the beefy brown brackets or outside the beefy brown brackets? Or inside? Or outside or inside? Well, it should technically be on the inside, right? Because that's where I just integrated. But when I distribute the 3/2 to c, what's 3/2 times c? New and improved c. ShamWow c. So you can actually put it at the back. It absorbs the 3/2. There you go. That's it. Power reducing identities. That'd make a great quiz just to ask you to regurgitate those. Maybe a quiz right after lunch. No. I can just threaten a quiz and then we wouldn't need to have one. Regurgitation quiz after lunch? That just doesn't sound appetizing. Yeah, exactly. Yeah, I knew what I said. I was just waiting for a reaction that never came, and that was good because that shows y'all's maturity. I'm the one that needs help. All right, we'll pick up here tomorrow, and we're done for the day.